Hello everyone. In this video, I am going to cover chapter 12, section 12.1 and 12.2. So here's an overview of mechanics. Mechanics is the study of how bodies react to the forces acting on them. In your statics class, we study the bodies in equilibrium. In dynamics branch of mechanics, where there are two parts. Number one, kinematics, which concerned with the geometric aspect of the motion, and number two, kinetics, concerned with the forces causing the motion. A particle, when it's travel on a straight line, we're going to define the coordinate axis S. So in other words, we're going to use S to define the position of the vector, position of the particle. So the position of the particle at any instant relative to the origin O, we're going to use this position vector R or the scalar S. Scalar S can be positive, it can also be negative. Typical units for R and S are the units of length: meter, feet, meters, feet, inches, centimeters. But just keep in mind that there will be the length of the unit of length. And then the displacement of the particle is defined as its change in position. Vector form, you have delta R equals R prime minus R. Scalar form, you have delta S equals S prime minus S. So the total distance traveled by the particle is a positive scalar that represents the total length of the path over which the particle travels. We learned this in physics class. Velocity is a measure of the rate of change in position of the particle. Velocity is a vector quantity. It's got magnitude and direction. Magnitude, if we're looking at the magnitude only of the velocity magnitude portion of it, we call it the speed, which it has the unit of meters per second or feet per second. Average velocity is the how much the particle uh, during a period of time, the particle, the total during this period of time, the total distance over the total time. So average velocity, V average equals change of the distance divided by change of the time over this period of time, how much we travel. Instantaneous velocity is the time derivative of the position. So, in other words, during this period of time, your velocity could change any moment. But however, instantaneous will be, if from your calculus, from the time derivative at that at any frac of that second, what is your velocity at that instant? So v equals dr over dt will be the derivative of position over respect to time. Now, the speed is the magnitude of the velocity, only the magnitude portions of it, regardless what the direction is. Speed is the magnitude of the velocity. Average speed is the total distance traveled divided by the elapsed time. So velocity, average total distance over the period of time interval. Acceleration is the rate of change in the velocity of the particle. It is the vector quantity. Acceleration's vector, meaning it's got magnitude and direction as well. Typically, the velocity, the unit for the acceleration will be meters per second square or feet per second square. Similarly, if we have instantaneous velocity over here, we got instantaneous acceleration as well. Instantaneous acceleration will be the time derivative of velocity. We're taking, on the previous slide right here, we take the derivative of velocity that gives me the acceleration. If I take the derivative of the position, that gives me the velocity. Taking the derivative of velocity gives me acceleration. So your first equation here, velocity form A equals dv over dt, derivative velocity with respect to time. And in the scalar form, In the scalar form, we have acceleration equals dv over dt, and also ds squared, the second derivative of a position over time. Okay. Now, acceleration can be positive. It can be also negative as well. Under the condition that acceleration is positive, we are increasing the velocity. So the speed is getting bigger. We're going faster. Under the condition that we have negative velocity, sorry, negative acceleration, that means the speed is decreasing. We're slowing down. Over here, the last equation, where in case if you wonder where that comes from, based on this equation right here, acceleration is dv over dt. You can, let's put another ds on top and on the bottom, okay? And the reason I'm doing that is I am going to look at this two together. ds over dt is going to be velocity. So in other words, dt, derivative of the position with respect to time, that gives me velocity. Velocity times dv, and then ds. Okay, now I am moving this ds to the other side of the equation. That gives me a ds equals v dv. That is the last equation right here. That's where that comes from. Um, Here's a summary of kinematic relations for the rectilinear motion. We're going to take the derivative of the position to get the velocity, take the derivative of the acceleration, sorry, take the derivative of the position gives me velocity, take the derivative of the velocity gives me acceleration. And if we go backward, we're taking the integral of the velocity will give me the position, integral of the um, acceleration will give me the velocity. A lot of times in our physics note, like to put a subscript zero after it. So S0 and V0 here, that zero represents the initial position, initial velocity. That zero stands for when t equals zero. Initially, what's happening? What is the condition at the very beginning when t equals zero? Now, here are the three master equations. You probably seen it before in your physics class. When we talk about we're taking the integrals, right? Under the condition that acceleration is a constant. That's a typically a classic example will be free fall. Under the condition that we have a free fall motion, acceleration will be dg 9.81 meters per second square or 32.2 feet per second square. That would give me these three equations where velocity equals initial velocity plus acceleration constant times time. Distance equals initial distance plus initial velocity times time plus 1/2 acceleration constant times t squared. And then velocity squared equals initial velocity squared plus 2 times acceleration, and then multiply by the change of the distance. Here's our first example. It says a particle travels in a straight line to the right with a velocity v equals 4t minus 3t squared meters per second. The t is in seconds. Also, s equal to 0 when t equal to 0. We're looking for the position and acceleration of the particle when t equals 4 seconds. And here, what's given to us is that velocity is a function of time. We can take the derivative of the velocity, this one right here, take the derivative of velocity with respect to time. First derivative, that will give me the equation of acceleration. That will give me, look, I'm taking the derivative of the velocity. This portion is the velocity that's given to us in our equation. Derivative of the velocity with respect to time. First derivative, that will give me the acceleration and equation relationship between time and acceleration. That means acceleration changes with time. We're looking for the acceleration when t equals 4 seconds. Now, when you get this equation, plug in t equals 4 to get our acceleration. And it's negative 20 meters per second squared. And we also looking for the position. Position, we're going to go backward. We're going to take the integral. Integral of the velocity over this period of time. Okay, so taking the integral of this thing, okay, we get 2t squared minus t to the third power. And we know that distance is a function of time as well. And we're looking for t equals 4. Plug in t equals 4. That gives us distance equals negative 32 meter, or 32 meters to the left. Another example here, we have a sandbag dropped from a balloon ascending vertically at a constant speed of 6 meters per second, and the bag released with the same upward velocity. So in other words, the balloon's going up with a constant speed, while the balloon going up with this constant speed 6 meters per second, I am going to drop a sandbag from the balloon. Okay. And then 8 seconds later, when t equals 8 seconds, 8 seconds later, the sandbag is going to hit the ground. We're going to look for the speed of a bag as it hits the ground and the attitude of the balloon at that instant. We know that the only acceleration is going to be the gravitational acceleration. So that means it's going to be constant acceleration, 9.81 meters per second squared due to gravity. And in this case, you know that usually we like to define going up as positive, but since it's free fall, going down positive, we define going down positive will help us um, run our calculation so that a lot of the numbers can be positive instead of negative. Okay, so we define going down negative. Um, the distance that the bat travel, starting with the zero, initial position zero, velocity zero times time plus one half acceleration a constant times t squared. So you have zero, and then the bag's velocity, initial velocity of the bag is -6, since we define going down as negative. That initially we have the bag or the balloon going up with 6 meters per second of the speed. That means you have -6 times 8. Okay, -6 meters per second times 8, because it takes 8 seconds to come down, and then plug in the rest, 1 half acceleration 9.81 times t squared, a squared. So this will be the total distance that the bag traveled during this 8 seconds. And then also, this is the total distance the bag traveled during the 8 seconds. But however, we're looking for the attitude of the balloon, not the bag, at that instant. During this 8 second, the balloon still keep going up. What we just calculated is the total distance that the sandbag travels since the moment that they drop from the balloon. Balloon itself keep going up after we drop the sandbag from the balloon. So okay, so 8 seconds with a constant speed of 6 meters per second. The balloon traveled 48 meters upward. So we're going to add these two numbers together. Okay, 265.9 plus 80 plus 48. Adding these two together, that gives me the total distance, how much attitude of the balloon by the time the moment that the sandbag hit the ground. Next thing, we're looking for the speed of the bag as it hits the ground. Again, constant acceleration. But we define going down positive. Velocity equals initial velocity plus constant acceleration times time. Initial velocity is -6 because we define going up, going down positive. So that means going up. Initial velocity going up will be a negative value, and then plus acceleration times time. That gives me the total final velocity, the moment that the back hit the ground. 8 seconds later, the velocity is going to be 72.5 meters per second going down. Okay, hope that helps you. This is what I want to share with you in this PowerPoint. Thank you for watching.